Measurement for the sake of physics in the eras before electricity was a feat that required both curiosity and mental fortitude, but the reward was enormous for those who persevered. If you've ever been interested in the history of physics, you've probably heard of the Cavendish experiment, which measured the gravitational attraction between heavy spheres made of lead to determine the density of the Earth. What many people don't know is that it wasn't the first time gravity from an object had been measured. A similar experiment had already been completed 23 years before, with one big difference. Instead of using lead spheres, it used a mountain. The key concept of this experiment is called universal gravitation, which Isaac Newton first hypothesized in his groundbreaking book Principia in 1687. The idea is simple. Mass creates gravity, and the strength of the gravitation is proportional to how much mass there is. Universal gravitation worked very well to explain the motion of the planets and moons in the solar system. But people were skeptical. They wanted some experimental evidence for such a bold claim. The only problem was that the amount of mass required to produce any measurable gravity was extremely large. Newton himself actually considered in Principia how a mountain would produce a small gravitational pull. He knew that the effect would be very small, and thought it would be impossible to measure. It took more than 50 years for anyone to try, and almost a century before an actual result was obtained. What made this measurement so challenging was how small the gravitational pull of a mountain would be compared to the gravitational pull from the Earth. An experimental method was devised to measure this tiny difference. A plumb line, which always hangs in the direction of the pull of gravity, would show the direction of the combined pulls from the Earth and the mountain. A telescope would be aligned with the plumb line so that it would be pointing upward along the same direction. Then a measurement of the position of a known star would be taken. The difference between the measured and expected positions of the star would be from the mountain pulling the plumb line away from true vertical. The angle between the plumb line and true vertical could be used to determine the ratio of the masses of the Earth and the mountain. The mass of the mountain would be estimated through surveying and rock density measurements. Since the volume of the Earth was known, the final result would be an estimate for the density of the Earth. Newton's laws had been published decades prior, and astronomers had already used them to estimate the masses of the other planets in the solar system relative to the mass of the Earth. This single measurement of the deflection of a plumb line would fill in the blank required to estimate the masses of the other planets in the solar system, along with confirming Newton's universal gravitation. The first attempt at such a measurement took place in 1738, 51 years after Newton published his theory. The measurement was conducted by a pair of French astronomers, using Mount Chimborazo in Ecuador. The telescope they used was too small for the task, and the quality of their measurements was so hindered by the difficult terrain and adverse weather that they did not express confidence in their measurement. 3 decades later, survey results for the Mason-Dixon line in eastern North America were producing confusing errors that always seemed to be in the same direction. A member of Great Britain's Royal Society, Henry Cavendish, realized that the errors could be caused by the gravitational effect of the Allegheny Mountains nearby. If it could be proven that mountains affected surveys, it would be something that future surveys would have to take into account. Universal gravitation meant that gravity wasn't just a celestial phenomenon that explained planetary motion. It was everywhere, and it could affect property lines. Over the next few years, Neville Maskelyne, the Astronomer Royal of the Royal Society, became convinced that conducting an experiment to measure the pull from a mountain was worthwhile. He proposed that a mountain in Great Britain be used to perform the experiment, which, if successful, would doubtless do honor to the nation where it was made and the society which executed it. The Committee of Attraction was formed to select the best mountain to use. To ensure the accuracy of the measurement, they wanted an isolated mountain with an east-to-west ridge and steep slopes. The Scottish mountain Schiehallion was found to meet these requirements and was chosen as the location for the experiment. In 1774, Neville Maskelyne performed the experiment at Schiehallion Mountain in Scotland. Using a 10-foot telescope and a pendulum clock for timing, he took a total of 337 measurements from both sides of the mountain to ensure his result would be accurate. When the measuring was complete, he began the careful process of calculating the small deflection of the plumb line. After finding a deflection of 11.6 arcseconds, or just 3,000ths of a degree, he computed the density of the Earth was about double the density of the mountain. A more accurate estimate would require a detailed survey of the mountain, but this initial result was a cause for celebration. Newton's theory of universal gravitation had been confirmed after more than 8 decades, and it wasn't just for planets. In 1776, Charles Hutton surveyed the mountain to compute its volume and mass so that Maskelyne's result could be improved. The work was tedious, and after 2 years he published his results. These included estimates for the mass and density of the Earth, along with the other planets in the solar system, as well as speculation regarding the metallic core of the Earth. Universal gravitation had enabled these scientists to understand far more than the motions of the planets. The understanding of gravity had allowed them to learn more about the planet and solar system they were a part of without leaving Great Britain.